Hello everyone. So much exciting research here at New Mexico Tech, and this is our contribution. This is the work that I have done with my collaborators Jay Castone and David Raymond. And we work on tropical cyclones and specifically rapid intensification. So, as we know from the news, hurricanes are a major problem. Major TCs pose threat to economies and lives, and one of the problems that we are tackling now is rapid intensification of these storms, where they intensify over 30 knots in 24 hours. And we still don't understand this problem well. 83% of these North Atlantic TCs undergo RI and threaten the US and other countries. So, to tackle this problem, we participated in the Tropical Cyclone Rapid Intensification Project, TCRI for short, from 2020 to 2023, and it's still ongoing, still results coming out. And it was an Office of Naval Research partnership with NOAA, National Center for Oceanographic and Atmospheric National Oceanographic and Atmospheric Administration. So NOAA flew standard flights that they fly every year with their G4 aircraft, and ONR contributed with 2 P3 aircraft. So every morning during these intensive periods, hurricane periods, we would wake up and have a meeting and to decide whether we are going to fly into this storm, what kind of modules, the P3 aircrafts, which are loaded with instruments and modules, which paths are they going to fly. And P3 aircrafts fly about 3 kilometers, 10,000 feet. G4 aircraft is our preferred airliner, flies 13 kilometers. And the reason why we love the G4 is they drop these drop zones here shown on the right. They measured the pressure, temperature, wind speed, and location of these zones throughout the troposphere, so it gives us a deep picture of the troposphere. We had, in this period, about 50 flights that were very useful for us, with 49 flights from previous field campaigns that we added to this data set. So how does one of these flights look like? Here we have an example of Milton from last year, which did a lot of damage, and you can see there's the storm in this infrared image on 93 west and 22 north. And the black circles show where we drop zones from the G4 aircraft. So we focus on this region around the storm and produce a 3D variational analysis where we interpolate the data in such a way that it satisfies an elastic mass continuity constraint. So it's very physical, not just linear interpolation between points. And this is very useful for calculating fields like vertical mass flux, which I'll talk more about. And one important point is we don't use model. This is pure data, just those drop zones is what we use. So what we are trying to understand is how rapid intensification happens, what conditions support rapid intensifications, and predictors for strong convection that we found that are very important in these cases are these two: saturation fraction, which is precipitable water divided by saturated precipitable water. That basically means the saturation of a column of atmosphere. 0.5 means 50% saturated with water vapor, 0.9, 90% saturation. And instability index, which is a load to mid-tropospheric moist convective instability. It's basically for, it measures basically saturated moist entropy difference between two layers. And these two quantities tend to be anti-correlated. But this is why they matter. So in our previous research, we've shown that if you have an area that has lower instability index and high saturation fraction, that affects how the storm, how the cloud looks like. And specifically, what happens with lower instability index, the maximum of vertical transport of mass is lower in the troposphere. By mass continuity, that makes convergence in lower levels stronger. So it brings more, whichever quantity, more moisture, more vorticity to spin up the storm. So that's why instability index and saturation fractions are so important. And I want to illustrate this on an example of Milton from last year, for example. You see the storm track up here, and on the bottom we have the wind speed in black, and pressure, central pressure in red. The wind speed is the maximum sustained wind speed in the hurricane. And you can see it went from a tropical depression to a tropical storm quite quickly and then transitioned into a hurricane. And what we want to focus on is Milton 2 and this rapid intensification period end of October 7th that happened, increased more than 30 knots in less than 12 hours, not even 24 hours. And let's take Milton 2 and see how the 3D VAR looks there. So here we have the 3D VAR for Milton 2. On the left is the mass flux at 4 kilometers. And the way that we identify where the storm clouds, where is the stormiest, is by taking the maximum of that. And that's denoted by this red box. And here in the middle, we have saturation fraction and instability index. And by the way, the red dots are these drop zones that we use. This denotes where we did the 3D VAR analysis. And so you can see that saturation fraction is very high and instability index is low in this case. So we do this for 99 flights that we did over the last 4 years and all the data that we have from before. And this is what we get. So here we have saturation fraction versus instability index. And each dot is one 3D VAR analysis. And first thing that pops out, there's an anti-correlation. The lower the instability index, the higher the saturation fraction for the convection. The second point here, we can isolate cases, 3D VAR cases for which the storm intensified intensely, and here is covered, it's 20 knots per 24 hours with the green stars, and rapidly intensifying cases with magenta stars. And what we notice, focusing on the rapidly intensifying cases, they occupy a really small area here in this saturation fraction and stability index space. Instability index is low, but not too low, and saturation fraction is high, but not too high. So there's a sweet spot of this phase space that supports rapid intensification of tropical cyclones. And this work we published last year in GRL. So this is the troposphere. And let me just add another point of something that's well known. You probably all heard that when the sea surface temperature is high, hurricanes tend to form and intensify. And that was also with this data here. And on the right here, we have the instability index, which represents the troposphere, and the sea surface temperature, which represents the boundary condition, the warm ocean. So what we see is with high sea surface temperatures and low instability index, that supports rapid intensification and intensification in general. And just note also that sometimes we had years where we had really high sea surface temperatures and hurricanes didn't develop as much. Well, that could have been because the troposphere was not really supportive of rapid intensification or intensification in general. And sometimes we have low instability index and low sea surface temperature, so that area is also unsupportive of intensification. So that's our recent result, and our future work is including, and we're currently doing some numerical modeling, idealized numerical modeling, and running weather prediction models on one particular storm right now. And we want to, this data set right now is 99 flights, but we are going to be adding more flights with each new season as it comes. We already added 12 flights from 2024 plus extra flights from field campaigns from 2008. And we want to expand this, the satellite data that we have from infrared to passive microwave and other data from satellites. And we are trying to put this into a form that easy for machine learning to maybe help predict rapid intensification instantaneously if possible. Thank you.